Okay, so we'll go ahead and get started here on a Friday. And as we're now sort of in the meat of the material, in the thick of it, we'll just dive right in and continue on from where we left off last time. Okay? So if you remember, we were last time calculating input resistances, input capacitances, and starting to understand the time dependence with which neurons could change their membrane potentials. And that's going to be very important in terms of signal, the information transfer from one neuron to the next via potentials. Okay? So we've so far just considered this membrane potential in and around the cell body, which we've modeled as a sphere. But now we need to really look at how those signals conduct along axons and dendrites. And just to sort of set up our physical room model here, again, let's pretend that over by the marker board is one neuron, and it's sending an axon over here to a synapse, the presynaptic side. Then over here we have the postsynaptic side. Neurotransmitters conduct across that. A dendrite then comes into me, and I'll play the part of this postsynaptic neuron. Okay? And so for that signal over there in that first neuron to reach me, it has to come down its axon, and it has to come down the dendrite into me. Let's ignore this, the synapse for the time being. Okay? So what about those signal properties in those long wire-like elements? All right? And it turns out that distance matters quite a lot in this case, not unlike wires in electronics. And if you consider the synaptic potentials at the dendrites conducting towards the cell body and ultimately the trigger zone, the axon hillock, we note that the cytoplasmic core is highly resistive. In other words, that solution that's on the inside of the dendrite isn't like a metal wire. Okay? It's a resistor of some sort. Okay? And the longitudinal flow, meaning down the direction of that dendrite, okay, is particularly resistive. And that's due to the small cross-sectional area. In other words, this dendrite that's coming into the cell over here is very tiny. And it has to be very tiny because you need to pack a lot of neurons in per unit volume, or your brain inside your head and so forth. Okay? So the resistance due to ions colliding in that narrow tube is really what gives rise to that resistance. Okay? And for those of you that this may help, it's like looking at why mobility is as it is for electrons, for example, in a semiconductor. And it's because there's lots of collisions with the crystal lattice and so forth. So things basically bump into each other. That's the fundamental nature of it. So what we need to actually calculate what these resistances are, and again, why are we putting all this in place? So we can actually understand how long it takes a signal to go from the first neuron to the second neuron. Otherwise, we won't understand how quickly signals can go across the brain or down to our feet and so forth. And we wouldn't understand how to design systems to interact with it. Okay? What we need is a so-called incremental length equivalent circuit. So yet more equivalent circuits. And each segment has its own measurable membrane resistance, Rm, its own capacitance, Cm, and each segment also has its own axial resistance within the cytoplasmic core, Ra. Okay? And again, for those of you that this helps, great. It's very akin to an electromagnetic transmission line, okay? Where all of a sudden wires don't look like just nice wires as we typically first learn them when you're operating at super high frequencies. Okay. So this is what that equivalent circuit looks like. Okay? And just to jump to the chase here in this figure, this is that dendrite, and we can chop it up into these little length segments. Okay? And you could imagine doing this in a continuum. So this is actually some length over which you would integrate, or you could imagine doing it discretely. And what you have is you have a Cm here. This is the membrane capacitance between the inside and the outside across that membrane. This is the resistance, and we're very familiar with this because this is what we studied last time, right? There's always a parallel RC element. And then there's a resistance along the length of this dendrite, RA, and that's that axial resistance. Okay? So this circuit gives us the ability to solve, and don't worry, we won't, either here or in homework, okay, or on exams. That's more about the math of it than the understanding of the science and engineering of it in some ways. But it's possible to then get a voltage across this membrane as a function of length and of time for any current that you may inject into this, given the elements here. And what we're more concerned with is, should these values be high or low? And if they're supposed to be high, how does the nervous system make them high? And if they're supposed to be low, how does it make them low? To, for example, increase the speed of transmission. Okay? So there are, just for your background information, there are simulation packages, a couple of which are called Neuron and Genesis, that allow you to really specify all these parameters and to solve for it directly. Okay? This is that bit about the project I mentioned you don't need to worry about. Okay? And finally, again, this is very similar to in semiconductor electronics. If you really want to model how electrons are colliding with the lattice, the super detailed geometry of every transistor, how it affects things, there are industry standard simulators for circuit and process. Okay? So let's now consider some special cases of it. Okay, let's consider the case where we take a length of this dendrite. We take our now very familiar apparatus, experimental mock-up, whereby we can impale the dendrite with one electrode and pass a current into it. Okay? And again, just to sort of cut to the chase with the diagram before we go through the left side here, if you spritz in some current here, what you might expect is there to be more current that comes back out of the dendrite here, meaning closer to where you inject it, than way down here. And the intuition for why that makes sense, hopefully it's intuitive, okay, is that for a current to go all this distance, it encounters all of that axial resistance, right? So if this neuron over here sends a nice action potential down an axon, crosses the synapse, and then comes down the dendrite, it has to come, let's say, many centimeters down this highly resistive small tube. And it's harder for it to do that than to come a short distance and then exit out of the cell, depending on the exact values of these three circuit elements. Okay? And that's indicated by the thickness of these purple arrows. There's no reason that it should be different to the left or to the right. Okay? And therefore you see the symmetry here. And that's what you might expect the form of the current coming through the membrane to look like. Okay? Why are we doing this? We could do a million different experiments, right? Just to try to connect it back, as I try hard to, every few minutes. This is like a current that's coming in from the previous neuron. We need to know how that current is going to spread in order to start to understand how a signal of some sort, like here, spreads over space and it's a function of time. Now, if you have a current distribution like this, you would also expect to find the change in the membrane potential to go accordingly, right? So you have some resistance, you know, and if you have more current going through it, you'll have a larger voltage drop. And that's why the delta Vm is at 100% here, and it decays. And one could, of course, solve for this exact form. Okay, so what we've just described is a case where we passed a current for some very long period of time, much greater than the time constant of those resistances and capacitances that we looked at last time. So we're at steady state. That capacitive current in this model here has gone to 0, right? Because we're at steady state. DC doesn't go through a capacitor, as we know. Okay. The overall current through the membrane is just the ionic current, okay, through the channels. And the potential distribution depends on the relative values of Rm and Ra. Remember Rm, going the wrong way. Rm is the resistance through the membrane, and Ra is the resistance down the axial length of the dendrite. Okay. So let's consider that at some point along this length, let's call it x, maybe we can define this to be 0, and over here, this is the x-axis. So this is some x here. So the resistance to go from here over to here is the axial resistance Ra per unit length times that length, so Rax. The membrane resistance at this point, of course, is just Rm. It's the same everywhere. You didn't accrue that larger Rm just because you went farther before escaping out of the dendrite. And therefore, the membrane potential at some point x is just Im Rm. Okay, the current going through the membrane times the resistance to go through it. So therefore, for this current injection induced change in membrane potential, right, we get a decay in this voltage, as shown here, that just goes as a single exponential, some net change times e to the minus x over lambda. Very familiar form. It's always a question, well, what is the lambda? And you can almost guess what it is. It's always going to be some ratio, and there's usually a square root. Okay? So it's square root Rm divided by Ra. Now, what I do want to spend time on, and that's what we're going to do in the next couple of slides, is not going through and solving all this. You've done that in your past. But to understand, should Rm be high? Should Ra be high? What should be low? And how does biology create it, as we were talking about? Okay? So again, these are just the same equations as before. So this is saying how the voltage changes down the length of this dendrite when there's some current injected at some point, right? So a better membrane insulation increases Rm. Okay, so let's root this back to our case in the room again, right? There's some neuron on the marker board, axon, synapse. I've said this 8 times already, sorry. Then there's the dendrite that comes to this other cell. What if that dendrite had some insulation wrapped around it? Okay, like the plastic insulation that we put around wires. That will increase the resistance. It'll make it harder for any current that's on the inside of that tube where the ions are flowing to escape it, right? Because we put a barrier there. Well, that might be a good idea, because if we increase Rm, we're increasing lambda. And if we increase lambda, we have to effectively have a much higher x to equal that lambda, right? And if we have to have a higher x to equal the lambda, that means that we're getting this deflection, this change in the voltage over longer distances. And why would we want a change in voltage over longer distances? Because if I'm this dendrite here and I get some change in my current here, I want to feel that signal. I want to receive that information way over here, a few centimeters away maybe, at the cell body. And I may not just want to do it from that one neuron that's communicating with me, but from another neuron and another neuron. I may want to listen to 20 different neurons. Remember this fan-in, fan-out stuff we went through? So for me to be an information processing element, I have to receive input from different sources, even though they may be different distances away. And if I can't feel that signal, I'm out of luck. Okay? And that's really a fundamental concept of the nervous system, a fundamental concept in the brain. If I want to see, I need cells in my brain to be able to take in information from a whole bunch of different pixel sensors effectively on my retina. So I need to be looking at signals coming from different points of spatial points on my retina and fusing that information together and making decisions like, do I see an oriented bar? Is it red? Is it green? And so forth. Same thing in the motor, same thing in your decision-making circuits and so forth. Does that make sense? Let me pause there. Yeah.
I was just wondering, I understand how like myelin would increase RM, but I don't understand why RA would decrease.
It wouldn't, with just that manipulation.
Okay.
Okay. That's a good thing to do, full stop. Another good thing to do, my transition, thank you. Another good thing to do would be to have a better inner core conduction, because that would decrease RA. Okay? I don't know how to do that. But if you had it, it'd be better, right? It's better to have gold wire, right, than, I don't know, what's some bad conductor? I don't know, glass, insulator total.
So how much control over the, essentially the resistance and conductance does the nervous system have? Because if you're going to pack on myelin and you've got different fan-ins and fan-outs, you've got to adjust the things so that you don't have different speeds in your essentially your logic networks, right?
Well, you may not want different speeds, or you may use those different speeds as effective delay lines, right? Okay, so a couple things are happening in the Q&A, which are great. But up to this point, we were talking about increasing that insulation, okay? And then we started hearing the word myelin pop up. We did talk about myelin already, but let's just remind ourselves that the way you can take a dendrite and increase its insulation would be to wrap it with myelin, okay? It's a fatty sheet that wraps around it, and that effectively blocks that conduction, okay? That doesn't typically happen, number two, on dendrites. That typically is reserved for axons, okay? Because dendrites are over shorter distances. The final point to the final question is, boy, if I was a neuron and I was listening to 10 different inputs, and I wanted to weight them all equally, right? Listen to these 10 different inputs the same, I better equalize a lot of things. I better equalize the way in which the previous neuron gets its signal across the synapse, which is often called a synaptic weight, if you've taken neural network classes, right? This is sort of the segue between what's neuroscience and what's machine learning based on neural networks, okay? But these weights, but you also may want to equalize, if there were myelin, you may want to equalize that so you don't have different conduction speeds. Otherwise, you'd be getting 10 signals at 10 different times, and that could really complicate your life. Okay? All right. So both of these would increase lambda, which would increase the ability to spread signal farther before leaking. Let's come back to our cylindrical dendrite of radius A, as we were looking at. Okay, we can calculate the axial resistance in terms of the cross-sectional area. So rho is the axial resistance per unit cross-sectional area. And you get that by taking and divided by pi r squared, or pi a squared. Okay? The membrane resistance is, again, just the total resistance divided by circumference 2 pi a. And if you put those together in this equation, you get the final form here, where you have an Rm over rho and A over 2. Okay? So what's this saying? Well, what it's saying is, coming back to this line here, I don't know how for the same unit cross-sectional area to increase the conductance. You'd have to have more conductive fluid, effectively. But one easy thing to do is to take your dendrite's circular cross-section and make it larger. Scale up A. And so you see that lambda does scale as the square root of A. And that's where it's coming from. And we've already talked plenty, I think, about Rm, where you want to increase Rm, which effectively is increasing cap R or decreasing A. Okay? But of course, because A squared, and this is just an A, you win net by having A go up. Okay, so thicker axons and thicker dendrites transmit so-called electrotonic signals farther. What's electrotonic? That's when you change the potential over here, and then it propagates, as we've been looking at, passively. Okay? So said differently, when you turn a voltage supply on an electric circuit, to just mesh our language, that would be electrotonic. that would be this. Because it's just a wire, maybe there's some R and C, some passive elements. You have not seen yet an active element, like a transistor where an external power source is employed. We will in a second. That's what action potentials are all about, okay? So what's a typical lambda? You know, something a little less than a millimeter, okay? So, signal conduction and neural function. This electrotonic conduction efficiency has two effects. The first is spatial summation. We've already foreshadowed all this, hopefully developed a lot of the intuition. Where synaptic potentials are generated in different regions of the neuron or added together at the trigger zone. Remember, we were talking that we want to, in the neuron, take in multiple inputs. By looking at how the voltages from my different inputs add together, because ultimately I have to have one voltage, and then comparing that voltage to some threshold, I, as the neuron, and particularly in the trigger zone, the axon hillock, may or may not decide to fire an action potential and send it out my axon to the next element. Okay? So the bottom line here is that the geometry and structure controls a lot about these electrotonic signal combination, propagation, and it's really a fundamental aspect of neural computation. Okay? This word doesn't exist. Propagation, local depolarization, okay, around, this is the region of action potential. So local depolarization spreads electrotonically down the axon, causing adjacent regions of the membrane to reach threshold. Okay, we'll go this more detail, but again, we're foreshadowing the action potential. And neurons with longer length constants have greater spread, and therefore they propagate more quickly. Okay, so I think this is the last. Okay, 3 more slides here. So let's unpack that last line, again providing, I think, now the third level of visitation to the action potential before we hit handout 6, which is the final full-blown version. It's like a 12-step program. There's actually like 12 key steps to action potential generation and propagation. And that's written out in handout 6 and the associated chapter. But let's look at passive conduction of depolarization. So what we're plotting here is voltage versus some distance along this dendrite. Okay? And we're just calling it a dendrite because it doesn't typically have the myelin. We don't have to get into so-called nodes of Ranvier where things are actively restored. And let's say that we have this pulse. Okay, not in time, but in space. You have this voltage profile where we're very depolarized here. Plus 50. This is down at more like resting potential, negative 60. So what we're used to, which is positive net charge on the outside, negative net charge on the inside, is flipped here. Right? I mean, if you have a positive 50 millivolts, you have to have positive on the inside of the cell. Okay? But out far enough, it has to flip back. So what's happening is that there's actually currents flowing. These positive charges, which are very concentrated here, will diffuse over here, both symmetrically. And the same thing here, positive to negative, positive to negative. Why positive to negative? That's just the convention of how positive current flow happens. Now, what will happen is that this pulse will move in some direction. Now, just from looking at a cross-section here, you could never tell if that's moving this way or this way. Okay? That symmetry will be broken, as we'll describe in the next handout, due to this inactivation state, okay, that we've teased ourselves with as being very important, but haven't put it all together yet. But let's say it's propagating to the left. Then you just see the same thing that's happening here, now happening over to the left. Okay? So clearly, the farther this voltage deflection can influence the cell here, you're getting longer range action. You'll be able to see this pulse farther along the dendrite, as we've been saying, is so important. Okay? And this little pop-up is, again, just a reminder of why it's moving from the right to the left on the page here. So what about the velocity? Okay? So let's say we have one of these action potentials moving. What about the velocity? Well, larger membrane capacitance requires more charge, of course. Okay? Requires more charge to change by the same membrane voltage or deflection in it, and therefore it moves slower. The action potential will move slower if the capacitance of the dendrite is larger. So the dendrite wants, if that's the right word, to have a lower capacitance. Okay? The larger RA also limits the current passing from one segment to the other and thus lower. Okay? Just reiterating what we've talked about before, this is written out in terms of two circuit elements. We won't belabor it. You're very familiar with this. We talked about this last time. This is a circuit element for one part of the membrane. This is for another. And if you talk about a pulse propagating, you can think about how current goes from one to the other. Okay? So let's put it all together in what I think is one of the more interesting things about handout 5, okay, which is to actually get these proportionalities correct. Okay? So we want to have fast action potentials for reasons we've talked about. Plus, it just seems like a good idea, right? Action potential speed is proportional to 1 over RA Cm. Okay, we can see that in the previous equations. We know that we want to keep axial resistance low. We know we want to keep the capacitance low. So there's two ways to do that. One we've already talked, actually we've talked about them both. We can increase the diameter of the axon core or the dendrite core, okay, for the following reason, okay. So ultimately we have that speed is proportional to the diameter if we go through it. And the second thing we want to do is we want to wrap the axon with myelin. These are those other cells in the brain and in the nervous system called the glia, which actually outnumber the neurons. So they literally come up and wrap themselves around axons, okay, and effectively increase the membrane thickness up to 100-fold. So instead of just being a few nanometers of membrane potential, which in a parallel plate capacitor formulation of epsilon A over D, the distance separating, now you could have hundreds of nanometers thick. Okay, so it really drops that capacitance. And therefore, speed is proportional to the thickness. Okay? All right, and then spreading. We saw that a few slides ago. But now something looks different here. It was the case, as sort of down here, that you had current coming out and coming back out of the cell most greatly closest to the injection site. But up here, it looks like there's very little current escaping until you reach all the way over here where there's no myelin, right? That's what this blue is. So it's doing exactly what it's supposed to do. By wrapping itself around this, it prevents the escape of the current and forces current to go farther before escaping. Okay? So for neurons with myelin, okay, or myelinated axons, in other words, action potentials that are triggered at non-myelinated segments of the membrane at the axon hillock. So what am I talking about? Well, it turns out that you cannot create a voltage pulse in the middle here. It has to start at one of these gaps between the myelin, and that's what's called a node of Ranvier. Okay, so a node of Ranvier is located at one of these gap sites, okay? And the second is, I'm not sure, yes, okay, so it's this node. These nodes are chock full of voltage-gated sodium channels, okay? And what happens there is that because there's so many voltage-gated sodium channels, if you have a small deflection in the membrane potential, you'll actually start that positive feedback cycle that we've talked about and create an action potential. So action potentials will start at these nodes of Ranvier. And then what will happen is that this current can discharge the capacitance of the myelinated axon segment ahead of it. Okay, so let's imagine that it is moving here in this direction. So that current will influence out to some spatial scale here. The myelin sheath is interrupted every millimeter or so by these bare patches. And that's where these voltage-gated sodium channels are in very dense existence. Okay? And the final point here is everybody's heard of multiple sclerosis, I believe. And this is a so-called demyelinating disease. So if you have an axon where there's supposed to be myelin, but it's gone, as shown here, what you see is that an action potential, for example, could be propagating very nicely in this direction. We'll talk about speed in a sec. But because there's no myelin here, that signal can't keep going. All of the current to provide the oomph of that signal gets outside the cell in such a short distance that it can't make it down to the next amplifier or node of Ranvier. Okay? So the signal peters out, in other words. Okay, I'll answer your question. Just one second, or I'll hear your question. We'll see if I can answer it. The final thing is a goofy plot, but it's the plot the book has. It's trying to bring out speed, but this axis is actually, if I can read it here, the time between the stimulus and the arrival of the action potential. Time between the stimulus and the arrival of the action potential. Okay, so it's some propagation time. Okay, so it makes sense. It's a correct plot. It's just an odd axis here. So what it's saying is, let's look here to here. Okay, it takes a very little amount of time. So the rise over run here, right? The rise in this segment takes very little time to go a very long distance. So the speed here is high, right? Okay, and the speed here being high makes sense because you've got myelin going. Now over here, you see that it actually takes quite a lot of time to go a short distance, so the speed is slow. And that's because you're traversing this unmyelinated region here. And we know that unmyelinated regions are moving purely electrotonically. And the capacitance is so much higher because you don't have myelin. Okay? The axial diameter is the same, but you don't have myelin. So this is actually just a speed plot if you decode it consistently with the axes. Okay.
Are the axon pellets / trigger zones subsets of the class of nodes of Ranvier?
We're using them totally interchangeably. So a node of Ranvier is located here and is number 2 packed with sodium channels and so forth. I think you're right. Technically, we're just going to use them interchangeably. By that, what I'm meaning is that the nodes of Ranvier are really meant as these little areas here where a signal makes it to it, that voltage is still deflected enough that it opens up these sodium channels and it causes that positive feedback, so it builds the signal back up to the big action potential that it is. And that's a node of Ranvier. A trigger zone, or an axon hillock, okay, can be another part of the cell that is just dense with sodium channels, that may be closer to the cell body. So in that sense, they are distinct, but loosely speaking, we're meaning the same thing. Yeah. Okay. So we're basically, well, we're done with handout 5. Except for just pointing out what I already pointed out last time, which is the last 4 pages here, just go into writing out exactly what I think is confusing in terms of the sign convention used in the book and why you want to use absolute values if you do it that way. Okay? So instead of going through all this, which is just gory, it's very readable for those of you that had circuits backgrounds. Okay, so in what I think is probably the most fun lecture, though I shouldn't, in the first half of the class, though I shouldn't say that because now you're like, oh, wait a minute. The rest of the lecture is going to be really boring. But this is where we finally put it all together, okay? So we can stop foreshadowing things, but hopefully we now have all the constituent parts in place so that it's really easy and intuitive to stick it all together and just see it really written out, hopefully very clearly, how we generate and propagate action potentials. All right? So the reading is here. We know that neurons carry information long distances and can do so only because of action potentials. Those are the only signals that make it, you know, tens of centimeters and beyond, okay, or even a centimeter and beyond. We just looked at electrotonic signal propagation, and action potential generation is the other, or propagation is the other flavor of signal propagation. Okay? Action potentials, which are also called APs or spikes, they're called spikes because they're very sharp deflections. So if you look at a time base of, say, a minute, they just look like these little vertical deflections on an oscilloscope, okay? Sort of a colloquial term. So action potentials are a regenerative electrical signal whose amplitude does not attenuate when it moves down the axon, okay? We have this in place, and now we're going to consider voltage-gated ion channels, these sodium channels we were just talking about, which are critical for generating and propagating these potentials. Okay, so we've seen it before, but what does an action potential really look like? Well, here we go. It looks like a signal coming up and then back down, then overshooting and coming over here. Now, what's this axis? This axis is the membrane potential. And what's this time scale? You can think of this as being about 1 millisecond. Okay, so why am I showing such a horrible plot? Well, this is the first time it was ever seen. Right, so that's pretty cool. And by seen, what I'm meaning is the first time it was ever seen in conjunction with understanding how it arose. Okay? Understanding that the fundamental mechanism is that the ionic conductance, these channels that open and close, as shown here and here, are really somehow so similar to the action potential that they have to be involved. Okay? So how are action potentials generated? Well, the ion conductance is high during an action potential. Okay, so ion conductance, well, that may sound a tad mysterious. We're just talking about more sodium or more potassium flowing through the ion channels. That's more the language we've been using. Okay, we know that that conductance is high. You can see it right here when the action potential is high, right? So here's the action potential, here's the conductance that's high. So this is the first evidence that action potentials result from that change of ion flux through the membrane channels. But again, let's put ourselves back in time, right? 70, 80 years ago, okay? Which ions? Right? So, right, if we turn off this slide and we forget about what we've just learned, okay, and I throw you a squid, literally a squid, right? The first thing you should do is fry it and eat it as calamari because they're delicious. Okay. Trying to wake you up on a Friday. Okay. But again, they have these beautiful big axons, right? And that's why they're an animal model of choice. You can just literally go get them out of the ocean and go in the lab and study them. Okay? And that really is, a lot of marine life is like that. Okay? And you sit it on your lab bench and you've got an oscilloscope, you've got some things, but you know, and maybe even have the clue that there are these little things called ion channels as we know them. Which ions, right? Well, it turns out you need to be a little bit of a chemist, right? Which is personally disappointing to me because I never really liked chemistry. But you have to be a little bit of a chemist because what you're going to need to do is you're going to need to shut down some ion channels to allow others to be seen. Okay, we'll get to that in a moment. Okay, and you also need to be quite a lot of an engineer, because you need test instrumentation that was first being designed and developed in around a lot of these experiments at the same time that they were starting to be more prominent and more available for all the electronics industry, right? Remember, this is, I mean, let me just put this year, 1938, when this was first seen back in your mind, right? This is pre-World War II. There were no digital electronics, right? Right? This is era of Hewlett and Packard, right? A couple of our famous alums, undergraduate alums, no pressure, okay? Be the old HP, not the new debacled HP, but anyway. This stuff was hard. The instrumentation that we'll see, we'll look at now and go, oh, of course you do that. Okay, well, you didn't know what to do. The electronics were hard to build, and you had to be sort of multidisciplinary. You also had to know some chemistry to piece it all together, okay? So hopefully that with that little historical reminder, it's easier to appreciate what we'll see here, okay? So a big clue as to which ions came from the following. If extracellular sodium, the concentration thereof, was low, then the action potential amplitude was low, right? So they backed off the salt, basically, outside the cell, and they saw the height of this shrink. Huh. So maybe the reason it goes up as high as it does has something to do with sodium concentration, right? So maybe sodium is responsible for the rising edge and the peak of the action potential. And Hodgkin and Katz, a couple of famous scientists, their data pointed to potassium also being involved, but being involved with this falling edge here, okay? So these clues burbling up from the literature, from scientific meetings, people are trying to piece it together, okay? So to test these hypotheses, what you really need to do is to go in and measure the actual sodium and potassium conductance as a function of the membrane potential, okay? Now that's quite a mouthful, right? Let's make sure we appreciate why that's quite a mouthful. You've got the clues that sodium and potassium may be major actors in this play. And you have to go watch them doing their thing while a very short 1 millisecond long pulse is happening, where as the membrane potential changes, more of these ion channels open or close, which then couple back into the membrane potential in that positive feedback loop we've been talking about. And that's going fast, so how in the world do you stand a chance? All right? And that's what's shown here. The problem is that the membrane potential and the ion conductance are coupled, right? You depolarize the cell, meaning you change the voltage up to maybe, let's say, plus 20 millivolts, for example, instead of the negative 60 or negative 70 that it likes to live at. That will cause sodium channels to open. That will cause an inward current. That will cause further depolarization. So how do you basically walk up to the neuron and say, okay, I'm on to you. I know that sodium and potassium are important to you. You're going to do your little dance faster than I can observe you. But I'm going to find a way to basically, at my will, I will exert my experimental will, right, freeze you at any point in the membrane potential curve, and then see which ions are flowing. And if we can do that, then we understand the sodium and the potassium so-called conductances as a function of time, as a function of membrane potential, and then we know how it works. Okay, so it's a lot like if I gave you a flip-flop, okay, and said, here's an oscilloscope. I'm going to give you a flip-flop, and it's going to be clocked at 2 gigahertz. Good luck. You tell me how it works, right? The first thing you're going to want to do is control the clock, right? You're going to say, no, I got to slow this thing down. I got to slow it down. I got to have more ability to probe that circuit to really piece together what's going on. So this voltage clamp is the solution. This is the electronic side of the solution. Okay, and the remaining 5 minutes, I think we'll get through a couple slides here, but wherever we're at when time ends, we'll stop. The voltage clamp decouples Vm and the opening and closing of the voltage-gated ion channels. It does so by injecting current into the axon that's equal and opposite to the current flowing through the voltage-gated ion channels. Okay, so it sounds like some sort of circuit that's monitoring the voltage and the current and controlling the voltage. Okay, thus the membrane charge and Vm do not change. So you can specify what Vm you want. The circuit will flow current, electrical current, into and out of it necessary so as to hold it at that Vm. Otherwise, if you ticked Vm up, additional current would flow through those newly opened channels, and that would further increase Vm, remember? This is the first time we're seeing our ability to set Vm as we wish. The current supplied by the voltage clamp, again, this magical device that we haven't seen yet, but will on the next slide, is a direct measure of the current flowing across the membrane. So all we have to do then is look at our instrumentation and look at the current that we have to supply, and then we know how much ionic current is going through those channels that are open. Okay? And by using this device, they were able to provide the first complete description of the ionic mechanisms underlying the action potentials, and it was sort of important. Okay, so let's leave with a couple diagrams here. Okay? So this is the core idea. This is what the more elaborated instrumentation looks like. Okay, so now I throw you that squid again. And you say, aha, I've got a clue as to what to do. I'll go grab the squid's axon. I'll impale it with one electrode down the center. Okay, so I can control that potential along that whole length. Okay, and it'll be uniform. I'll put another electrode outside in the solution of my little beaker that I've thrown the axon into. Okay, and I'll have this device called a voltage clamp, but basically what it'll do is it'll allow me to dial in that I want a Vm of, you know, negative 30 millivolts or negative 20 millivolts or positive 20 millivolts. And then some current will flow, and I'll measure that current, and then I'll know how much current's going through those ion channels. Okay, that's sort of the block diagram, boxology sense as to how this works. Okay, just one second. This is the more elaborate version. This looks the exact same as over here. Let's fill in what that voltage clamp really is. Again, the current meter also looks the same. Well, what's really going on is that you put two electrodes, one on the inside of the cell. That's what this one is. When it's sharp, it's meant to mean it's impaling. And you put the other one on the outside. Okay? And you hook this to an op amp, right? An amplifier. So the positive one goes on the inside of the cell, the negative one goes on the outside. Why? So that this is Vm. Vm, as we define membrane potential, Vm, is the voltage on the inside of the cell minus the voltage on the outside of the cell. So this respects that sign convention. It then goes to the negative terminal of another op amp. And you have a signal generator where you can dial in Vm. And why is it a signal generator instead of a voltage supply? It's just so you can change it in time. You can put little pulses of voltage in if you want. That will cause this voltage to be the commanded Vm. That may in turn cause channels to open up. Okay, and you'd say, so current's got to flow. Where does that current come from? Well, this op amp, of course, can source a huge amount of current. It can put out as much current as is needed to subserve those newly opened channels. How much current is there? You're going to measure it right there. So all of a sudden, you can dial in the Vm you want. You can measure the current going through the ion channels you want. And that's the electronic side of it. We'll pick up the story next time where we'll put on some blockers, as they're called, to shut certain ion channels down. And then we've got the triangulation. We can say which ion channels are flowing that current and which are not. And then we can piece the whole story together. OK, not Monday, holiday. See you Wednesday.